Swayam Prabha. Digital India. Educated India.
Hi, welcome to the course of structural biology again. We are in the new module, but we are still continuing with structural biology techniques, and we are all still continuing with X-ray crystallography. Remember, we have talked about the invention of X-ray and what X-ray is doing. Now, we will start where actual business is, how the X-ray would be produced. So, for production of X-ray, power is sent to the X-ray tube via cables, and then milliamperage is sent to filament on cathode side. Filament heats up, electron produced which are negatively in charge, and then positive voltage is applied to the anode. Negative electrons are attracted across the tube to positive anode. So, now electrons slow down and finally come to rest. Electron beam is focused from the cathode to the anode target by a focusing cup. So, when it is on the rest, it is targeted. The distance between filament and the X-ray tube target is 1 centimeter, and suddenly the velocity of electron raised from 0 to half the speed of light. So, first we produce electron, allow it to go to rest, then focus from the cathode, and the velocity of the electron is high. Now, the projectile electron, now it is about the travelling from cathode to anode. The projectile electron interacts with the orbital electron of the target atom, and this interaction results in the conversion of electron kinetic energy into thermal energy mostly, and electromagnetic energy in the form of infrared radiation and X-rays. So, the energy, electrons kinetic energy through the movement is now giving us X-ray, but the thing is here in the tube the heat produces 99% and X-ray is 1%, and the X-ray is Bremsstrahlung characteristics X-ray, but the main concern here the production of the heat which is 99%. We discussed about the properties of X-ray. Let us took a refreshed look. Electromagnetic radiation is generally 0.1 nanometer to 10 nanometer. Wavelengths typically for XRD application is 0.05 nanometer to 0.25 nanometer. That means 0.5 to 2.5 angstrom. That is where most of the atomic interactions actually exist, and 1 nanometer is 10 angstrom. So, if you see that is the reason I talked about, but this is again very important to remember. X-ray is used because the range of X-ray is in the range of atomic distances, the bond distances. If you look at in protein, there is carbon, nitrogen, oxygen mostly, and those are bonded within 1.5 angstrom around. So, that is why X-ray works perfectly. So, we understand how X-ray generate, but what are the instrumentation through which X-ray generation is done? One of them is Coleridge tube or cell tube. Here if you see, this is the picture, you see that heated filament emits electron by thermionic emission. Electrons are accelerated by a high voltage, copper rod for heat dissipation, and X-ray produced when high speed electron hit the metal target. So, copper is used as a metal target, or different metal target could also be used. The entire X-ray generation system is sealed into one unit, thus eliminating the need for vacuum pump motor to spin the target. So, we talked about different aspect. First, the generation of electron, then to use it to speed up from focusing through the cathode, and then it again goes. So, all the process in the seal tube are in one unit. So, you do not need other things. The system is therefore very compact and easy to maintain. The tube is water cooled to dissipate heat. Most seal tube are lower power to avoid overheating the target. So, you cannot generate powerful X-rays because with the increasing energy requirement, the heat generation would also be enhanced, and that is not good for the safety of the instrument, hence safety of the experiment. Rotating anode, which is commonly used, these are the same idea as a seal tube, except the anode is spinning at 6000 rpm, allowing a much greater loading to be put on the target since the heat is spread out over a larger area. Rotating anode is a derivative concept and it is the mostly used X-ray source. Here the modification, the critical modification is, instead of making it static, there is a rotation happened, and because of the spinning which is around 6000 rpm, it what happened, the heat dissipation happened. So, higher energy X-rays are possible to generate. A 2-pound copper target spinning at 6000 rpm places some stress on bearing and seal. So, the target is 2 pound and it have to continuously rotate at 6000 rpm. So, it creates stress. The vacuum system is no longer a single assembly and typically has 2 different pumps. Wear and tear is significant and maintenance becomes a more serious issue. The state of the art for macromolecular rotating anode sources is a Rigaku generator, which is a lower power but high brilliance X-ray generator. For long time, Rigaku generator is giving us good data collection in home source. So, it is a proven method. In both seal tube and rotating anode sources, the wavelength is fixed by the characteristic emission spectra of the target material. Copper is one of the most often used for protein since it is having an efficient conductor of heat, and the CuK alpha emission is relatively intense than other metals. The wavelength of X-ray produced by copper is 1.54 angstrom, again very much at match with the bond lengths. Small molecule crystallographers typically use weaker molybdenum sources. They do not need that much intense source what we need to solve the protein crystals. So, they typically use molybdenum instead of copper with a wavelength closer to 0.7 angstrom, since the higher energy X-rays are absorbed less by the experimental mount. So, it is the generation of Bremsstrahlung radiation. Bremsstrahlung radiation means breaking radiation. Electron deceleration releases radiation across a spectrum of wavelengths. The breaking radiation represent a continuum. So, if you see the electron comes and heat and it slowed down and change the direction. This process releases a quantum or photon of radiation that has a wavelength characteristics of the energy difference between the cells. So, when it hit, a electron like release and the other electron comes and match the hole. The designation K, L and M correspond to the quantum number 1 to 3. Alpha and beta indicates the cell that the filling electron is from relative the vacancy cell. So, from here to here it is alpha, from here to here 2 jumps it is beta. K alpha indicates the photon that is released from an electron transition from the L cell to the K cell. So, it is K, L and M. So, if it is K to L or L to M, this is alpha. If it is K to M, this is beta. Here the electrons suddenly decelerate upon colliding with the metal target. If enough energy is contained within the electron, it is able to knock out an electron from the metal atom's inner shell. That is what we want, and this is an unstable state, and this vacancy is quickly filled by an electron from the higher shell. Through this transition, we get the energy. Generation of characteristic radiation. Not every electron in each of these cells has the same energy. The cells must be further divided. K cell vacancy can be filled by electrons from 2 orbitals in the cells for L. So, K, L and M. So, when there is a vacancy in K, this would be filled by L and then M. Energy levels of the electrons, as I talked about, K, L and M. So, when one jump it is alpha, when 2 jumps it is beta. The intensity ratios of alpha 1, alpha 2 and beta is 100 to 50 to 20. So, this one is the most efficient. Here you see this is K alpha and this is K beta. Emission spectrum of an X-ray tube. Different metal provide different wavelength. To get a different wavelength, simply change the composition of the anode. We must have a source of monochromatic X-rays for X-ray diffraction. We must try to eliminate white radiation and K beta radiation to use only the K alpha. If you look at when you use copper as anode, K alpha 1 is 1.54, K alpha 2 is almost 1.54 and K beta is 1.39. Whereas, when you use molybdenum, it is K alpha 1 is 0.70, K alpha 2 is 0.71 around and K beta is 0.63. The characteristic wavelength is 1.54 and 0.7. 1.54 is used for protein crystal and 0.7 is used for small molecule. In this slide, I will not talk about science, but I want to just let you know what a beautiful group was there in University of Munich in 1912. Röntgen, you already heard about. He was the director of the physics laboratory. He have invented X-ray and changed the world's recognition or detection or device development. Arnold Sommerfeld, he was the director of the Institute of Theoretical Physics. He did experimental work on wave nature of X-rays and his contribution is greatly helped us. Paul von Groth, professor of mineralogy. As you know, mineralogy have contributed to X-ray diffraction in a huge way before protein crystallography field have arrived. Actually, the starting of X-ray related research started on minerals, and then looking at the characteristic foundation, people have also start exploring protein. So, you could say protein crystallography actually is a derivative, is a like coming out from the research of mineralogy. Paul Peter Ewald, you all will see him later for Ewald's sphere. He was a student of Sommerfeld working on propagation of X-rays in single crystal. We will talk about him. And Max von Laue, he was a Provajonet, which means a lecturer with not a permanent position in Sommerfeld's institute. X-ray diffraction, As I told von Laue designed an experiment in which he placed a copper sulphate crystal between an X-ray tube and a photographic plate. You could see that this is the setup of Friedrich and Knipping's improved setup. This is the diffraction photograph. Friedrich and Knippings, they are the they are assisting von Laue for the experiment. After a few initial failures, they met with success on 23rd April 1912. X-rays passing through the crystal formed the pattern of bright spots that proved the hypothesis was correct. The hypothesis of that when you have a crystal, you pass X-rays, you get a meaningful spectra. That is what the kind of birth of X-ray crystallography, the diffraction. The crystals can be used to diffract X-rays. So, you have X-ray source, you have crystal and you have a diffraction pattern. This is diffraction from where you get the spots and you calculate the pattern to get some atomic information. Data collection strategy and data processing. So, now we have come far away where they have heated crystals and got diffraction. They need to collect more data and they need to process, and the phenomenal development here is by father and son Henry and Lawrence Bragg's. It is called famous Bragg's law. In 1913, William Henry Bragg and his son William Lawrence Bragg derived a formula to explain the diffraction of X-rays by crystals. They won Nobel Prize in Physics for their seminal role in X-ray crystallography. So, let us take a look what they had actually done. This is kind of a animated representation of a crystal. You see the molecules in the crystal lattice. Now, if you have seen the phases, now if incident light would come, what will happen? The light come and the ray will reflected in different direction. If instead of a crystal which makes the thing complex, you consider incident planes. So, an incident wave with a certain wavelength strike the planes 1 and 2. So, it strike 1, it strike 2, okay. And as in a crystal, every planes are equidistant and the distance is d. So, if you see, they come and they are reflected. So, if you see the angle is theta and the path distance is AB and AC. So, AB and AC vertical with lights A and A prime respectively. So, the path difference of rays from adjacent plane, how you get? You will see that here there is a perpendicular triangle formed and you get an angle which is theta. So, and the distance is d and this distance is BD. So, the path difference for rays from adjacent plane is BD, this one plus DC, this one. Now, if you put the trigonometrical formula, sin theta would be BD by AD, AD equal to D. So, BD by D, So, BD equal to D sin theta. Similarly, DC is also the same. So, BD plus DC equal to 2 sin theta. When the waves are coming, they could be in destructive and constructive interference, and you need constructive interference for the work to continue for the detection. So, 2D sin theta equal to k lambda, where k is 1, 2, 3 like integers, and this is Black's law. 2D sin theta equal to k lambda or n lambda, where k or n is an integer. This relation helps us tremendously in the field of crystallography. This is the home source from Regaku for protein crystallography. You could see that here is the detector, and here you could put the crystal. Here is the camera where you see the crystal and you could align. But I talked about home sources are relatively recent development. Before, the data used to be collected in synchrotron, but now synchrotron is even more and more coming useful to the crystallographers. So, it is called that macromolecular crystallographers have increasingly hijacked the high energy physicists' toys to use them as ultra bright X-ray sources. Synchrotrons are large tubular rings under high vacuum in which fundamental particles, usually electrons and positrons, zoom at velocities near the speed of light. I repeat, synchrotrons are large tubular rings under high vacuum in which fundamental particles, usually electrons and positrons, zoom at velocities near the speed of light. I say large tubular ring. Can you imagine how big is this large tubular ring? Generally, where synchrotrons are developed, it is a tiny town and the beam covers the entire town. Now you could understand. So, if you are in a small town and your town contains synchrotron, so you will get a circle. The whole circle is surrounding your tiny town, small town, and that's big the magnet is. The rings are really just polygons, since relativistic particles are kind enough to obey Newtonian physics in at least some regards. Why? So, electron, positron, they are like going to be in a perfect ring, rather than they have this broken ring from where these are the magnetic field and X-rays coming out through windows. The positrons, electrons travel in straight lines until forced to turn a corner by powerful magnets, and those corners are actually called windows. So, in the windows there are beam lines. I was working in Argonne National Lab, APS, where we used to work on circuit beam line. So, in every synchrotrons they have certain beam lines where crystallographers work. They go there and they collect their data. We will talk later when we will talk about the speed of collections. Now, the home sources are relatively getting better, but when I started my career, let us say 2004, 5, 6 to even 2010, normal Rigaku crystallography diffraction machines, they used to take around 3 to 5 days to get a complete data set. In comparison, synchrotron take 20 seconds for one frame, which means around 20 minutes for the entire data. For home sources, it takes used to 10 to 30 minutes for a frame. That was the difference. Fortunately, the difference is also getting reduced day by day. At these beam bending magnets, some interesting things happens. It costs energy to deflect, change to momentum of all those particles. That energy gets returned to us in the form of intense electromagnetic radiation when the particle change direction. A lot of this radiation is in the X-ray band, and we can use it as a remarkably powerful X-ray source. Even more powerful X-ray source can be formed if one put insertion devices in the straight stretches of the particle beam. So, generally it is powerful, but what people do, what advancement do, they use something called wigglers. Wigglers make the beam do just what wiggle up and down. As a result, the velocity is changing, electromagnetic radiation is produced, but these devices are designed to produce a lot more local deviation in the trajectory before returning on the original path. So, wiggler act as X-ray sources much brighter even than the bending magnets. A typical wiggler is engineered to extremely high tolerances, features superconducting magnets and is a few meters long. So, you see the change. While the bending magnet is covering a whole tiny town, these are few meters long. So, that is the beauty of the wigglers. Here I am giving you some example of primary synchrotron sources. In US, the National Synchrotron Light Source NSLS at Brookhaven National Lab BNL at New York. The Advanced Photon Source APS I just mentioned about at Argonne National Lab in Chicago, Illinois. The Cornell High Energy Synchrotron Source Chase at Cornell College. Advanced Light Source ALS in Berkeley, California. Stanford Synchrotron Radiation Lab SSRL in Stanford, California. Other notable ones include Diamond from United Kingdom, ESRF from France, Photon Factory from Japan and Anstro from Australia. But that is not the end. For interested people, I have given a link. You go to the link and you get all the description details of all the synchrotron present in current world. I talked about, remember, that a synchrotron beam is like covering a tiny town. This is Argonne National Laboratory. I did my PhD in University of Illinois, Chicago. So, we used to go there, and as you see, this beam is covering the whole kind of small town. Coming to symmetry in crystals, why do we need to know the symmetry of the crystals? Because we reduce the size of the asymmetric unit, which is a unique part of the crystal. We will go and discuss what is the asymmetric unit. Reduces data collection by reducing the number of unique reflection to collect. Symmetry may be useful in phase determination. We will discuss it when we will go to the data analysis section. International Table Volume 1 is considered as a Bible for crystal symmetry. We will discuss about that also. Periodicity and symmetry in a crystal. A crystal has long range ordering of building blocks that are arranged in a conceptual 3D lattice. A building block of minimum volume defines unit cell. The repeating units protein molecule are in symmetry in an unit cell. The repeating unit is called asymmetric unit. A crystal is a repeat of an asymmetric unit. So, if you see, you have a small molecule or a protein molecule. This protein molecule might be presented as one in the unit cell, two or many. They could be developed many symmetries, like if you see, it could be a cube. In the cube, the molecule might present on the corners, they might present on the face, they might present on the base, they might present on the, so its face, base and body. So you got simple cubic development, face centered cubic development, base centered cubic development and body centered cubic development, and they would be repeated to develop a 3-dimensional array, which is our crystal. So, we have discussed about the X-ray source, how X-ray generated, what are the home source and the like high powerful synchrotron source, and in the next we will discuss in detail about how this unit cell and symmetry is there and how it is different from normal molecule and protein molecule. You all are amazing audience. Thank you very much for your patience. Please listen to the courses. If you have any queries, please ask us, contact us, me and my TAs. They are here to answer all your questions. Thank you very much. I will meet you in the next class. Thank you.